Standard time series modeling is restricted by our tool's geometry. Clocks and calendars measure exactly two functions: duration and sequence. Applied to complex systems, recurring events appear chaotic. Pinned to a flat line, they look isolated and randomly distributed. A one-dimensional progression lacks the capacity to show how events align or repeat. It only records the distance between them. Without a geometric context, standard forecasting models often misinterpret rhythmic, cyclic signals as unpredictable noise. The Chronal Ruler framework, developed by Umair Abbas, moves away from this flat cartography. It treats time as a topology, the study of shapes and spaces. The mechanism relies on a mathematical transformation that takes linear time data and wraps it into a cyclic, multi-harmonic phase space. Once plotted onto these angular coordinates, chaotic points snap into structured alignments. These concentric rings reveal cadences that are invisible on a straight timeline. This allows for a different analytical objective, mapping the geometric architecture of time to detect hidden structural alignments. This topological model suggests that events separated by vast linear distances can occupy the exact same structural space. Bending a linear sequence into a closed shape requires this core equation. The variable t represents the incoming stream of raw linear time data. The result is theta, the calculated angular position on a unit circle, measured from 0 to 2 pi. This transformation is identical to the math used for angular position mapping in celestial mechanics. By treating time as a geometric value, the framework converts isolated dates into precise coordinates. In any phase space mapping system, the geometry floats completely aimlessly, without a fixed boundary condition to stabilize it. The variable t0 provides this stability. It is the chronal anchor that locks the system to a fixed origin point. This 0 point is what makes measurements across vast distances meaningful. This functions like the initial conditions in physics, or the WGS-84 datum that global GPS relies on to establish a spatial reference frame. With an agreed-upon anchor, researchers can perform a precise cross-comparison of events occurring in entirely different eras. The anchor ensures that topological geometry yields repeatable, comparable results across any scale. The final variable, p, represents the period. Time series data operates on many rhythms simultaneously. Like Fourier decomposition, this breaks complex systems into layered cadences. A single event maps to phase 0.5 in one cycle and phase 0.75 in another. Moving to a 3D harmonic lattice allows overlapping periods to be visualized simultaneously. This stacking reveals synchronicities entirely invisible on a flat calendar. A multi-harmonic space identifies vertical structural alignments across different temporal frequencies. The framework ingests massive volumes of historical data directly into its geometric grid. The system then applies spatial clustering algorithms like k-means and dbscan to the phase space coordinates. The resulting phase coherence score measures temporal resonance. This processing generates distinct, tightly packed groups of data points, even when the original linear dates were scattered. These points cluster together because they share phase coherence. This geometric proximity overrides their linear separation. The math demonstrates that structurally resonant events occupy the exact same geometric coordinate space, regardless of the centuries that divide them. This reveals the core premise of the framework. Proximity in geometric phase provides more structural information than proximity in linear time. Macrosystemic events separated by centuries align precisely once they are plotted within this topology. The Chronal Ruler maps temporal resonance. It does not calculate linear predictions or guaranteed causality. It is an instrument for pattern recognition, identifying when disparate systemic variables are vibrating in harmonic alignment. This temporal grammar is already being applied across several quantitative disciplines. Quantitative analysts are using it to move beyond fixed period cycles and detect dynamic phase alignments. In machine learning, state space models are being trained to recognize phase coherence rather than simple linear correlations. Biologists are reframing circadian and hormonal rhythms as geometrically phase-aligned systems. The Chronal Ruler provides the APIs to convert standard chronological data into a measurable architecture. We can now map, analyze, and navigate time as a resonant, multidimensional space.